In 6.2, we're going to be taking a look at another aspect of differential equations, and that pertains to a topic called slope fields. You can see a slope field pictured above, but I'll talk about more specific details concerning this picture in the coming slides. Okay, so let's first consider this differential equation. dy dx is equal to x plus 2y. If we were trying to do a problem like this back in 6.1, we would have need to been able to separate it so that we could solve it. So can we separate this differential equation? Well, you'll notice if I take the dx and multiply it to the other side of this equation, which is a typical step we take, we would kind of be stuck here. We need to get that 2y to the other side, but the only way to do that is to kind of distribute that dx, but there would be a dx attached to the 2y. So there really is no way to separate this differential equation. We can't get the x's and dx's by themselves and the y's and dy's by themselves. So we can't solve this differential equation in this particular course since we're only studying separable differential equations. So what if we wanted to analyze the solution to this differential equation with some other technique or tool? Well, that's where slope fields play a role. While we're not going to know the exact original equation or solution to this differential equation, really the particular solution, since we're not going to know that equation so that we could graph it if we wanted to see what it looked like, we can use the differential equation, the derivative, to build something that is called a slope field. And all a slope field is just made up of a bunch of line segments with slopes. So what are these slope fields useful for? Well, I guess first these slope fields illustrate how the tangents to the different solution curves behave. Additionally, and this is kind of the key here, slope fields can be used to analyze how the original equation, the particular solution to a differential equation, behaves. And since we can't actually find the original equation or the particular solution, this is kind of our only hope, so to speak, for now. Okay, so the way we plot a first order differential equation is just like you would plot functions back in Algebra 1. If I were to make a table of values, normally when you made a table of values, you would choose some x values and plug it into your function to get your y values. Connect the dots, so to speak, and then that would be your graph. Instead, for these things called slope fields, we're going to be plotting lines, little tiny line segments that represent the slope at those points. So I already have this table pre-populated for some of the points on this graph here that you see, and just to kind of illustrate how this table relates to the graph, I have 2 points here in particular that I'm trying to emphasize. You'll notice at 0, 0, if we were to take that x and y value and plug it into our derivative, we would get a derivative equal to 0, or in other words, a slope of 0. And it's a little hard to tell here, but that's why we have a little horizontal line here that represents a slope of 0. Additionally, if you take a look over at 0, 1, if we were to take 0 and 1 and plug it into our derivative, we would find that we had a value of 2. But since that 2 corresponds to the value of our derivative, which is a slope, we can take that slope and visually graph it with a little line segment. And you'll notice here it's not a super steep line, but certainly steeper than a slope of 1, and that's our slope of 2. So you can kind of see all these slopes visualized at all these points here on the graph. So how is this going to be useful in terms of us understanding what the solution to this differential equation would look like? Well, just like in 6.1, we would need a particular point, an initial condition, so that we could see what particular graph we were looking at amongst the infinite amount of graphs because of that plus c. So the first thing we got to do is plot a particular point and then use that to visualize what the graph might look like. So I'm going to go ahead and start at the point 0, 0. The way we can use this slope field to kind of determine what the original graph would look like, not the equation necessarily, but definitely the original graph, is to use these little line segments, which represent slope, to kind of guide us in terms of drawing our line. So I'm going to go ahead and put the line in here and kind of describe what's happening here. But as we move to the right, you'll notice that this slope is telling us to start curving upwards in a positive direction. This slope telling us to curve upwards in a more positive direction. And you can kind of see again these slopes kind of telling us to go up in that direction. To the left of 0, 0, we have this slope right here telling us to curve upward, but it's not a very steep slope, so it's still not too increasing. Here again, we have another increasing, or I guess decreasing in a way, depending, but I'm moving to the left. But either way, this slope is not very steep, so our line's not getting very steep, as opposed to the right side of this graph. So it's really that these little line segments, which represent slope, are kind of telling us what direction to go in. And that's what these slope fields are sometimes also called. They're called direction fields as well, because they kind of tell you which direction to go in. It's kind of pushing you in one particular way. And it's all about that initial condition. If I put that dot somewhere else, maybe the graph would look a little bit different. So let's take a look at a couple more examples of this. Here we have the differential equation y squared minus 2x squared. And just to point this out, we cannot separate this differential equation, so this slope field is kind of our only hope. Here I'm going to again look at the initial condition, the starting value of 0, 0. And if I draw this solution curve in, you'll notice to the left, our slopes are telling us to, stay not too steep, but definitely kind of go upward. This one's telling us to get even steeper, but we're still going upward and upward there. To the right, this slope right here is telling us to start decreasing down, but not at too steep of a slope. This slope is a little steeper, this slope is even steeper, and you can kind of see how this graph takes its shape. These graphs, don't be so concerned with drawing perfectly, so to speak. It's more about getting these graphs to be in the ballpark of what they look like. This is not an exact science. We're just using these slopes to kind of show us in what direction and shape, ultimately, that our original graph, the particular solution, would look like. In this next example, this differential equation is separable, actually, but we're just going to focus more on this slope field and understand what it looks like. And I'm going to graph a bunch of particular solutions here, just to give you an idea of, depending on where you start at, your graph will look a little bit different. If I start here at this point, this very topmost point here, our graph is not so curved, so to speak. But if I start down here at this graph, it's a little more U-shaped. And then, of course, the bottom kind of is the reverse of that. Again, these slope fields tell you the slope at certain points, or in reverse, you can find the slope of these slope field points by plugging in an x and a y value into your derivative. And you'll notice, just as an example, at 2, 1, if I were to plug that x and y value into our derivative, we would have a slope of 1. And you can kind of see that right here in this point, this slope field point that's circled. It has pretty much a slope of 1. So at the point 2, 1, the slope of the tangent line is 1. So ultimately, what I hope you take away from this is that building these slope fields is just a matter of plugging numbers into your derivative, finding the slope, and then drawing that appropriately steep line of steepness. And then, of course, these solution curves all depend on the point you're starting at. Okay, so let's take a look at that original animation from the title slide, and you'll notice that these two solution curves look very different depending on the initial condition you're at. If I use the initial condition 0, 0 here, you'll notice our graph in blue here looks like that when you're following the slope lines. If I were to graph a solution curve through this point here, this y-intercept, you'll notice the graph looks much different if you follow those tangent lines. So again, it's all about that initial condition in terms of the way your solution curve is going to look. Okay, so let's take a look at a couple AP questions. Remember, the key to these slope fields is that slope fields can be used to analyze how a solution to a differential equation behaves. And that really is the key here in this first example. We're given a slope field, and you can see the differential equation right right here. And we want to figure out if g of x is the particular solution to this differential equation. Using the initial condition -2, -1, we want to determine what the limit of that original particular solution function is as x goes to infinity. So of course this would be a really easy problem if they just gave you the graph of g of x, and then we could just look at the graph and see what's happening as x goes to positive infinity. But we're not given that original graph. We're given the derivative, or the slope field graph of this. And because of that, we need to draw that particular solution in as best as possible, and then we can maybe use that to figure out what the original graph would look like, and ultimately what the limit as x goes to infinity is. So you'll notice something, and a couple key slopes to point out here. You'll notice that y equals 2, if you were to plug that into your derivative, we'd get a slope of 0. And you can see that all along this y value of 2. When you plug in a y value of 2, this derivative becomes 0. Same thing for y equals -2. You'll notice this very important line of 0 slopes, because when you plug in the y value of -2, we get a slope of 0. There's one other important slope of 0 that we kind of see but don't see, and it's all along the x-axis. These little slope lines, when they're along the x-axis, if they're a 0 slope, they're pretty much impossible to see because, well, they're 0 slopes, of course. But I'm going to emphasize that. We realized that if we plugged in a y value of 0 into our derivative, we would always get a slope of 0. And that's going to be important as we look at the initial condition and try to draw that particular solution graph. So let's go ahead and plot the point, -2, -1. That is our initial condition. And let's let these slope lines dictate how we draw our solution curve, or the particular solution graph, if you want to call it that. So you'll notice, to the right of this point, these slopes are telling us immediately to go up. But the key is, and you'll notice, and that's why I emphasized along our x-axis we have a slope of 0, we're approaching a slope of 0. Our slopes start off steep, they become a little less steep, and then of course eventually they'll become a slope of 0. To the left of our initial condition, again we're going to have to approach a slope of 0 down here, and because of that, it'll never touch that, so to speak. It's an asymptote. So ultimately, roughly speaking, our particular solution would have a graph of something like this. And once we have that graph drawn in, now it's just a matter of using that graph to analyze what the limit as x approaches infinity is. And you'll notice, as x approaches positive infinity, we're approaching a value of 0. So ultimately, that would be the limit of our particular solution, which again, they're calling g of x in this problem. Another type of AP question that's very common on the free response will be to fill in a slope field. And luckily, it's just kind of tedious. Well, I guess shouldn't say luckily, but definitely easily it can be done, because we just have to take these points and plug them into our derivative. The tedious part, I suppose, is taking those values and plugging them in and not making a little arithmetical mistake. Being careful with your mental math, because normally these are done on the non-calculator section. So let's go ahead and try to draw in this slope field. At 0, 0, if I take that x and y value and plug it in, we'll get a slope of 0. And it's very important you really emphasize that that's a slope of 0 by drawing that horizontal line as flat as possible and not make it with any steepness. The other thing you'll notice, which is good, is that at any value along the y-axis, it's always going to be a slope of 0, since x would always be 0 on the y-axis, which would make our whole derivative 0. All of these slopes are 0. So luckily that's nice and easy. Now the tedious part just comes in of taking all these points and plugging them into our derivative and figuring out what that value is. And of course that value corresponds to the slope that you're going to draw, the line of the slope that you're going to draw. So don't forget this notation here. This notation again is just saying we're evaluating, that's what the bar means, we're evaluating the derivative at the point -1, 0. So we get a slope of -1, so we'll draw a kind of neutral slope, so to speak, right there in the middle of 1 or -1. On the other side, at 1, 0, we'll also get the same slope of -1. There's a little bit of symmetry going on here. At -1, 1, we get another slope of 0, and also on the other side at 1, 1, we'll get a slope of 0. At -1, 2, we'll get a slope of 1. So we'll draw that appropriately sloped line. And on the other side, again at the point 1, 2, we'll get a slope of 1. Here's the key to these slope fields. What happens when you get different slopes, like a half or maybe a 2 slope compared to the 1 slopes? Well, you just have to be careful to show that that line has either a steeper slope or a less steep slope, depending on the number you get. And in this case, when you plug in the point -1, 3, you'll get a slope of 2. So how do you draw an exact slope of 2? Well, you don't have to worry so much about that. We just have to show that that slope is steeper than the other slopes, relatively speaking, in a manner of speaking. So the way we need to draw it is not, again, perfectly, but if this is how you're going to draw a slope of 1, then relatively speaking, this slope of 2 would of course show a steeper line. As long as you do that, you'll always be okay when you're drawing these slope fields. And then again, because of symmetry, at the point 1, 3, we'll get another slope of 2. So I think these two examples kind of illustrate the approaches you'll be taking when doing some of the AP problems concerning slope fields. The last type of problem that concerns slope fields will be identifying slope fields from their differential equation. A very common kind of question is to be given a differential equation, and then the choices are for you to identify which slope field matches that differential equation. So we need to know how to read these slope fields to kind of match those. So one possible way to read a slope field is just one segment at a time. The problem with this is it can be time consuming. So maybe there are some more purposeful ways to approach analyzing these slope fields. So here's a few strategies that, if they work, definitely use them, and unfortunately, if I guess they don't fall into these categories, well, maybe just looking at it one segment at a time might be the only way to analyze it. Okay, so let's go ahead and take a look at a few examples here. What if you see a slope field where all the slopes are the same, vertically speaking? You'll notice all across this slope field, we have the same slopes vertically. Well, our differential equation then would only have x's in it. And in a way that kind of makes sense if you kind of relate that to graphing in a sense. If I were to tell you to graph x equals 2, you would graph a vertical line. In other words, that equation only has an x in it. So hopefully that little analogy will help you out here. But if you see the same slopes all vertically, that differential equation will only have x's in it. So I think it would probably be logical to guess this, but what if you see the same slopes all horizontal? And just to highlight one of those rows so you can see what I mean, then that differential equation would only have y's in it. What if you see the same slopes diagonally though? And again, I'm going to just highlight one of the diagonals to illustrate that. If you see a slope field where all it has is the same slopes diagonally, instead of depending on just x or depending on just y, in these differential equations, it'll depend on both. And it'll look in like two different forms. It'll look like either x plus or minus a y, or a y plus or minus an x. One other little trick that might help you in identifying these slope fields is what if you see a sinusoidal shape? Well, I think without having a picture here, hopefully you kind of remember a sinusoidal shape is just kind of this wavy shape. If you kind of see that general wavy shape, that differential equation will either have a sine or a cosine in it, depending on some specific points that might help you identify which it might be. Really, outside of these four, some key things to kind of look for is what would make a slope 0, kind of like you saw in that last slide. At some certain points, you notice that the slopes were always going to be 0. Or maybe there are some certain points that make your slope undefined, or maybe just positives, or maybe just negatives. When all else fails, kind of go back to what I said at the beginning. Just find specific points, plug in those points, and see what the slope is and see if it matches. Again, it can be time consuming, and if you're not careful, it can certainly backfire, but it'll always work. So hopefully all of these strategies will help you in the next slide to match up a differential equation with its slope field. Okay, so we have a bunch of slope fields here. We have a bunch of differential equations, and our job is to match up the right slope field with the appropriate differential equation. I'm going to use those strategies from the last slide to help us out in doing that. So you'll notice, and I'm going to kind of go in the order of the strategies from the last slide. You'll notice that two of our differential equations here only have x's in it. So the slope fields we'd be looking for would be slope fields that had the same slopes all vertically across the slope field. And you'll notice two slope fields here fit that description. In choice B, all those slopes are the same vertically, and I'm just highlighting two of the columns here just to point that out. You'll also notice in choice E, we have the same slopes all vertically across the slope field. So then which one matches with which? Well, you'll notice in number 1, x is being squared, which would mean x would always be positive. X would always turn out to be a positive value, which would ultimately mean the derivative will always turn out to be positive. In 5, x could be positive or negative, so our derivative could have positive or negative slopes. You'll notice in choice B, in the column I highlighted, these are negative slopes, these are positive slopes. In choice E, the slopes are always positive. So going back to that idea, number 1 would be choice E because the slopes would always be positive because the value of the derivative is always positive. In 5, it would be choice B because the slopes could either be positive or negative depending on what point you were looking at. The second strategy involved looking at the same slopes all horizontally, and that's when you had a differential equation that only depended on y's. You'll notice for choice C, the slopes are all the same horizontally, and for choice D, the slopes are all the same horizontally. So then we're going to need a little bit more critical thinking to maybe place which one goes with which. So let's take a look at C. You'll notice there's a slope of 0 which appears to be at 1, and then we have some positive slopes below the x-axis. On choice D, we have positive slopes at the top, and we have some negative slopes at the bottom. So I think the key here will be this 0 slope in choice C. If our y value is 1 here, if we were to take that and plug that into choice 2, you'd notice we get a value of 0, which is the slope line segments that we see there. So because of that, in 2, our choice would be C, and in 6, of course, our choice would be D. The third strategy we looked at is what if we have a differential equation that depends on x's and y's in either the form x plus or minus y or the form y plus or minus x. And you'll notice 4 and 9 fit that. So we would be looking for a slope field that has the same slopes all diagonally. And again, here I'm going to point out just a little bit of a diagonal just to emphasize what's going on here. So choice F has all the same slopes diagonally, and choice G has all the same slopes diagonally. So then which one fits which? Well, you'll notice on F, at this point here, I'm going to use red to kind of emphasize this, we have a negative slope right here on the y-axis. Here we have a positive slope here on the y-axis. And of course we can use any point we want, but I'm going to go ahead and use that to kind of identify what's going on here. We have a negative slope here at the point 0, 1, and we have a positive slope here at the point 0, 1. So then which one would be the appropriate choice for 4 and 9? Well, in choice 4, we're taking our x values and adding them. In F, we're getting a negative slope. 0 plus 1 would not be a negative number. But in choice G, 0 plus 1 would of course be a positive number. So then that of course means that G would go with 4, since that is showing us the positive slope there at 0, 1. So F must be the choice for 9. Why is that correct? Well, again, if that's the point 0, 1 here, and we're getting a negative slope, then that makes sense. 0 minus 1 is negative 1. So that would, of course, match with choice F. The fourth strategy that we looked at was what if you see a sinusoidal shape, or that kind of wavy-looking periodic shape? Well, we have two choices, A and H. So which one would go with cosine and sine? Well, again, looking at a specific point here is going to be the key, and I'm going to look at the origin. In choice A, we're showing a slope that is positive, and in choice H, we're showing a slope that is 0. So, which one's the appropriate one? Well, if we take an x value of 0 and plug it into cosine, cosine of 0 is 1. So of course, we're seeing a slope of, or a positive slope at the very minimum in choice A. So that would match with 3. In H, if we take that y value of 0 and plug it in, sine of 0 is 0, I see a 0 slope there. So of course 8 matches with H. A couple other little strategies or particular kinds of slope fields that you might see pertain to choices 10 and 11. In choice J, you'll notice this hyperbola kind of shape, and in choice K, you'll notice this circular kind of shape. It turns out that if you take x over y in the positive version, you'll end up with the hyperbola shape, which is choice J. When you take x over y but make it negative, you'll end up with a circular shape, which is of course choice K. Of course, number 7, just by virtue of process of elimination, would be choice I. But again, if you take a look at these slopes and analyze them as it pertains to x squared plus y squared, it would make sense. And you might be looking at all of these slopes as being undefined slopes. It actually turns out they're not undefined slopes. They're just very, very steep lines that kind of look undefined. The reason that these slopes are not undefined, and you can see over here since it matches with x squared plus y squared, when you take an x and square it, and the y and square it at certain points, those numbers can get pretty big, so to speak. Certainly once you get to like a 7 or 8 slope, it gets very, very steep. So of course, over out here to the outside, or to the further points away from the origin, the slopes are going to be very steep. As you get closer to the origin, or the smaller numbers, the slopes are not as steep, but they're certainly all positive slopes. So it does make sense that x squared plus y squared would match choice I, but it was kind of easier to come to that conclusion after this process of elimination. So that's kind of the last way slope fields are going to be useful. We can use them to analyze the solution curves, or the particular solution, what it would look like. We can use it to draw a slope field at certain points. And in this last slide, we can take slope fields and match them to differential equations using these strategies we've talked about.